So I think we'll start formally if all set from your side.
Yeah, we are all set.
Yeah, just so just to let you know that there are some 90 odd participants who have joined. Apart from that, we are projecting this in our computer laboratory. So there are few students who are associated with us through that, and I think some more would join as in some a few more minutes. And before you start, I would request one of our students, Arya, to introduce you, and then we may start with the session. Right.
Sure.
Thank you for joining. Thank you.
Yeah. Do you have
Good
any?
afternoon
Yeah.
all present here. I welcome you all to this highly anticipated expert session hosted by our esteemed guest Dr. Rimzhim Gupta. We are privileged to have with us today a true luminary in fluid mechanics and computational physics. Dr. Rimzhim Gupta, a distinguished expert from a PhD from IISc Bangalore, is renowned for her exceptional work in applying CFD techniques to solve complex fluid dynamic challenges across various industries. She is currently working as a research scientist at Paanduv application. Her major focus subjects include wastewater, water remediation, and reactor technologies for varying chemical processes. Today, she is here to guide our expert session, offering her wealth of knowledge, passion, and a unique perspective that promises to elevate our understanding of computational fluid mechanics. So, without any further delay, let us welcome Dr. Rimzhim Gupta.
Thank you, Dr. Joshipara, for this kind introduction, and thank you. Sorry, I didn't get your name. Thank you very much for the kind introduction. So let me just start with sharing my presentation. Let me know if that's visible to all of you. Yeah, I hope it's visible.
Yeah, it is visible. Yeah.
Okay. Okay, so this talk is going to be about computational fluid dynamics and its applications in chemical engineering. I'll be focusing more on sustainable practices for computational fluid dynamics because that has been our motto at Paanduv Applications. We are using those techniques which are sustainable in long run, and how we are providing such services and how we are doing it, I'll explain in upcoming slides. So I would also like to thank Department of Chemical Engineering and IICHE who has organized this event. Let me straight go to, okay, so few things which are left from my introduction. I'll just keep it short. I am currently working as a research scientist at Paanduv Applications. My past associations has been with Hindustan Petroleum R&D and JNCSR, which is a prime institution of fundamental research and sciences. My PhD is from IISc Bangalore, and my master's has been from Aligarh Muslim University. So I have that diverse cultural background during my experiences during my PhD and master's. Currently, I am handling chemical engineering related projects at Paanduv Applications, which are associated with energy, environment, heating, ventilation, air conditioning systems, thermal systems, as well as which systems that include reaction kinetics. And we are using OpenFOAM CFD to execute all our projects and all our work. So I have been using sustainable quite a lot, and you must be wondering, in computational sense, how sustainability is a matter of concern. When you talk about normal chemical engineering, sustainability has a heavy meaning attached to it because renewable energy concepts, zero liquid discharge, and various other concepts we are learning these days which are associated to sustainability. Sustainability is something that does not make a hole in your pocket, and which is having a higher longevity. That means it is economical, it has some social impact, and it doesn't have any harmful effect on environment. In the similar sense, if we talk about computational physics, the open source software that we are using for CFD, that the software name is OpenFOAM. That is economical because it is It does not have any license cost. It is zero cost associated with this. So it is economical. Now, how is it making a social impact? Because this software is developed by decentralized manner. That means researchers across the globe are developing something on OpenFOAM. They are an expert in this field, and then they are developing the software, and then we all from all over the world, we are using, and they are deploying those services to all the people. So that has been the social impact, because it is not limited to any country, any region. The countries which have lower economies, let's say for Iraq, Iran, these uh, countries are very doing a very good work using OpenFOAM. They are using OpenFOAM for their own good, and it has been exceptional usage of such software. On the environmental impact side, the software OpenFOAM does not have any harmful effect. That means it is scalable on cloud. That means it does not put any limitation on the number of processors you can use in your computer. So, in a way, the open source community or open source software, be it any CFD software, or take it an example of DWSim, which is an open source process modeling simulation, which is a kind of a replacement for Aspen. Uh, these softwares are free of cost, and this is for your own good that you start using these software. Let's talk more about the chemical engineering applications now. If you minutely observe all the unit operations of chemical engineering, it is all about mixing and separation. You take any unit operation: distillation, filtration, liquid extraction, solvent extraction, any technology or any unit operation you talk about. These are either mixing two constituents, or these are separating two entities. That means on the conventional side, we have these many applications: reactor technologies, separation technologies, mixtures, internals, HVAC and heat exchangers, and wastewater treatment. These are just some of those technologies that I have listed, with, which are using CFD at its peak. If we talk about unconventional technologies, which are coming into the picture now when the sustainability concept is introduced: battery, fuel cell, waste minimization, CO2 capture, zero carbon technology, renewable energy, and microfluidics are just some of those technologies. They are also exploring CFD to the fullest, and these have been very challenging problems where CFD can be very handy. So I have bifurcated my presentation in two ways. One, I will talk about sustainability, and second, I will talk about the applications of computational fluid dynamics in chemical engineering aspects. Let us first understand where CFD comes from, what is its emergence and origination. CFD, computational fluid dynamics, is used to solve the fluid flow problems, and basically we use Navier-Stokes equation to solve these kind of problems. This It has its emergence and analogy taken from Newton's second law. When you try to derive the conservation of momentum using shell balance equation, uh, that's where you get this whole equation. And if you take the analogy from Newton's second law of motion, the units are analogous to mass, acceleration, and force. On the force side, you have viscous forces, you have pressure gradients, and you have forces due to gravity. So Navier-Stokes equation, if you see this previous equation, it has dependence on velocity and pressure. That means there is a pressure velocity coupling, and that is the reason that analytical solution of Navier-Stokes equation is not available. So Navier-Stokes equation is one out of 6 unsolved math problems in the world. That's why A numerical technique was developed, which is called computational fluid dynamics, to solve the Navier-Stokes equation, and that's where the computational fluid dynamics emerges from. On the right hand side, you can see a flow visualization of turbulent jet, and you can see how minutely it captures the details of the flow. Depending upon the parameters, how good the meshing is, how good other numerical schemes are, you can get as good as solution as you can see in this image. When one talks about computational fluid dynamics, everyone imagine a colorful image, uh, but CFD is not just a colorful image. These colorful images are the factual representation of data. On the background, I have a image where you can see different color schemes, and you will wonder what these color schemes are representing. On the gray color, you have these buildings, and in the diagonal shape, you have these dry coolers which have their outlet in the form of heat evolution from these particular units. When the wind is coming from the left hand side, how this wind is taking away all the heat and spreading it around the surrounding, it represents that temperature variation. So these colorful images are much more than just the colors and just the good visualizations. It is an amalgamation of mathematics, fluid dynamics, physics, numerical analysis, and computer programming. Let's talk more about, once we understood what computational fluid dynamics is and what it solves, we should understand the sustainable practice and how we can improve overall workflow in CFD. So we have two entities. One is commercial bodies and one is open source CFD, which the software name is OpenFOAM. OpenFOAM is a community that has been developed over a long duration of time, and uh, people and experts from different countries, different research labs are developing those solvers. Because they are experts, the newer research is going on every year, and those updates we get without any cost. So in a way, this is a whole community that has been working for good, working for deploying these softwares for all the community. Whereas commercial codes are limited, they are expensive, uh, and although they also have a user community, but you will find it very limiting in some sense, because they are providing uh, such tools where they are limiting with the number of core counts or number of cells you can use in your problem. So in a way, when you are in university, your university is getting the access to get those software for you, but when you are going out of your university, you don't have the access for those commercial softwares anymore. You can use the cracked version, but that's not ethical. So it's a very good idea that universities start promoting using open source software, so that students, when they are graduating, they should know what these softwares are. And let me tell you, industry is also migrating very rapidly towards open source community and open source software, because these are capable to solve challenging problems, and this has the liberty to go to the source code, edit the source code according to your customized requirements. Whereas commercial softwares have a GUI, graphical user interface. You don't know what's going on in the background, you don't know what equations are going on in the background. You are just a tool to click buttons and proceed further. So apart from that, OpenFOAM has other advantages as well. Apart from having the zero cost, you can customize the code. You have the access of code. The raw code of OpenFOAM is written in C++. I think you all must be aware of C++ coding. then that way you can get a good access of those codes and you can understand them very well. These are scalable on cloud. You, if you have a machine of 8 cores, you can utilize them as well. These codes and these solvers are accurate, and that proof we have put in our VNV manual, which is Validation and Verification Manual by Paanduv Applications. You can access this PDF at our website. This contain around 25 of the CFD cases from different industry: microfluidics, electric vehicle, automotive, aerospace, and whatnot. This also has a decentralized development. I have already explained what this is, and industry is rapidly migrating towards OpenFOAM. So there are more and more jobs available for students, for freshers, to explore CFD and OpenFOAM further in their career. Let's dig for some of the key aspects that open source community offers. Apart from accuracy, both have accuracy. If you access the uh, if you change the meshing, precisely work upon numerical schemes, etc. Software cost is completely zero, cost of upgrades is completely zero, cost of support is completely zero, consulting cost is completely zero, customization is very much possible, post processing is very much possible in both, and OpenFOAM has state of the art post processor attached to it, and you can access it very well. It's very easy to use. Cloud compatibility is available with both, but open source softwares are scalable on cloud. These are not. These will charge you extra money for using more number of cores. Research compatibility is there in open source software because it is completely customizable. Available expertise is available for both, and Pandav is one of the experts in open source community. Let's, if even if you are going for commercial software, one should know some of the key aspects before choosing the software. These aspects are: the software should have a license validity more than 6 months. Less than 6 months is completely not acceptable. Software does not should not have any limitation in terms of number of mesh count, number of cores, or cloud access. Support should be provided. There should be a user community of more than 10,000 forum threads on cfdonline.com. Sales angle should not be included. Software update should be accessible, and the software renewable process should be hassle free. There should be a VNV manual for any software that you are opting for, and you please cross check before getting on board with any software. Customization should be possible, and post processing should be possible. So keep noting all these points before uh, going for any software. So once this sustainability part is completed, we should move forward with computational fluid dynamics in chemical engineering applications. I have decided the flow of the presentation in such a manner. First, I'll be covering the data center part. Uh, on the industry basis, I have divided in 6 parts: data centers, hydrogen, microfluidics, water, reactors, and separation technologies. These all are a cumulative part of chemical engineering applications. Data centers, first of all, I'll cover that. So, in the current scenario, data is valuable, data is priceless. You all must be using social media platforms, be it Facebook, Instagram, Twitter, LinkedIn. I don't remember any other name, but they are posing different challenges in saving the data in the data centers. They are saving all their data, all our data in data centers. And if there is some discrepancy on uh, ha- uh, higher of the temperature of the servers where the data is being saved, the data can be lost. So the challenges in data center industry comes with the cooling of the data centers, which cooling mechanisms one should go for, which cooling units these data center should use, what should be the cooling locations, how the heat island effect in data farms can be minimized. These are some of the problems that data centers are currently facing, and we have solutions to all those problems. On the physics side, data centers include HVAC, which is heating, ventilation, and air conditioning, thermal management, and heat recovery. And CFD has all the solutions for all these problems. See, let me tell you, CFD is being used by data center and social media companies in a wide manner. Their dependency on CFD is increasing more and more with the challenges that data center community and data center industries are facing. So this is a CAD. This is an electrical room where you can see four data servers are kept in a horizontal manner: UPS 1, UPS 2, UPS 3, UPS 4. Two of them are working. That means two of them are uh, uh, rejecting some heat, which is around 63 kilowatt of power. UPS 3 and UPS 4 is not uh, generating any power. So these are not the heat sources. These will just be considered as walls. STC1, STC2, 3, and 4, these are just the boxes which will also be acted as the walls. ARU1 and ARU2 are the two cooling units. They are confused whether these cooling units should be kept here in a frontal manner or they should be kept in a longitudinal manner as shown in the right hand side figure. So these cooling units have their outlet at the top and their inlet at bottom. In the current scenario, this blue color thing, outlet, means that cold air is going in the room from these outlets, and hot air from the room is coming from these inlet, which is at the down. Logically, hot air will have a tendency to go up because of the buoyancy effect, because of the density of hot air, and cold air will have a tendency to go down. Whereas here, the hot air inlet is at the bottom. That means we anticipated that this configuration may not be good enough for these data centers. Let's see what these results dictate. So the methodology that we used to simulate these kind of problems, first we create the geometry. We use FreeCAD, which is an open source software for CAD creation. We create the CAD first, then we do the meshing using Snappy Hex Mesh, which is again open source software. This meshing is important because these methods are finite volume methods. We saw that we need to solve the Navier-Stokes equation by discretization. We need to convert this in grid format, and first in single grid the parameters will be calculated, and further it will be translated to more and more grids until the complete system is solved. Further, we will solve the problem. We will set up the case by providing boundary conditions in OpenFOAM, and we visualize the overall results in a meaningful manner in post processor, which is ParaView. So governing equations which are being solved in the background are conservation of mass, conservation of momentum, and conservation of energy, with a good amalgamation of correct set of boundary conditions. If your problem is transient, you will need an initial condition. But if your problem is spatially changing or it is a PDE in second order PDE, you need to provide two boundary conditions. In a similar manner, if you get a correct set of boundary conditions with correct set of equations, your problem case setup will be done, and your accuracy will depend upon how good the meshing is, how well you have provided the discretization, and how correct you have proposed the numerical schemes. So this case study, which is electrical room HVAC modeling, the problem statement is associated with reducing the overall temperature of the electrical room and minimizing the temperature which is coming out from the inlet of the cooling unit, which is the inlet. Uh, Objectives here are choice of the cooling unit, whether one should go for ARU, which is air rotational unit, or one should go for CRA. These both units have a different configuration of inlet and outlet that I'll be dictating later. Um, Cooling unit placement should be frontal or longitudinal, or uh, the optimal utility of the units. Let's say one unit is failed, only one is working, or what if both are working but at 50% capacity? So these all scenarios we simulated for world's largest social media company. Okay, we logically also, and uh, we got the solution for a frontal arrangement of ARU, and we didn't get much of the satisfactory results. So we went ahead with longitudinal arrangement of ARU and CRY units. The difference here in CRY unit is that the inlet of the hot air is at the top, which logically makes sense, and the inlet of the cold air, which is coming in the room, is at the bottom, which logically makes sense, because uh, hot air will tend to move upward and cold air will remain at the bottom. And we got the results for that. We simulated CRA units, both arrangements, when they are working at 50% capacity, and we got the best result for that scenario. You can see the average temperature is around 89.5 degree Fahrenheit. Cold air sitting at the bottom. There is complete stratification of gases of the cold air and hot air at top and bottom. And maximum temperature is also reduced in the in comparison to the previous scenario, which is for ARU. And if you see these tables, there is a complete um, sense of uh, establishment for CRY units, which is comparably very less. The overall temperature, the average temperature, the outlet temperature of the hot air, it's completely different. And CRY units is far better than ARU units. The physics used here is turbulence, heat transfer, and buoyancy effect. Yeah, so this is already established that CRA unit for 50% capacity, both in the longitudinal way, showed us the better results. Now, there has been another problem in data centers. When you take a uh, large areas of data centers, these are called data farms. In these large areas, there are units like dry coolers, which try to recover the heat which is coming in from the liquid, which is used to cool down the data servers inside the data centers. So this heat recovery, during this heat recovery, the heat is evolved and dissipated in the surrounding by dry coolers. So one needs to take care of from which direction the wind is coming, and if there will be heat island effects generated in the surrounding areas, because that is not acceptable. Urban heat island effects are generally when you have these materials of construction, that is concrete, some cemented materials, they tend to reflect more heat rather than much of it that is being absorbed. If you take a comparison of green surfaces and the concrete surfaces, you will always get a higher temperatures for these city areas where you have all the concrete, all the furnished, cemented materials which are being used. So these are called urban heat island effect, which is very prominent in data center areas. The problem statement here relates to the difficulty in designing an optimum dry cooler arrangement for maximizing the cooling efficiency. And we needed to see the effect of wind, which is coming from one direction, what should be the speed, and with different wind speeds, how the scenario will be, how the temperature thermal scenario will be. So this is the domain, these DCB2, DCB1, ADM, these are the buildings. Chillers are kept, and these blue are the dry coolers. These dry coolers, if you, these are the zoomed images of these dry coolers. The outlet is at the top, the hot air is going out in the surrounding from these particular pink uh, surfaces, and these yellow surfaces are the inlet. The colder air or the wind which is coming in, which is available nearby, is coming in to the dry coolers by these yellow surfaces, and the wind is coming in from the bottom. So these are the contours. You can see these are the volume rendered images, where for 5 miles per hour, 15 mile per hour, and 25 mile per hour, we simulated the three scenarios. And for 5 miles per hour, the heat island effect is quite prominent. Whereas for 25, the wind speed is such that it is taking away all the heat completely away from these data center or data farms. If you see in this plot, for 25 miles per hour. Okay, so the second part is about hydrogen. You all must be aware of water splitting reaction, where water is converted into hydrogen and oxygen in availability of sunlight. This application is widely explored in this particular scenario because we are promoting more and more usage of renewable energy sources. In this particular application, in this particular work, this work was done for BITS Hyderabad, and in this particular work we have used a semiconductor material as photocatalyst, which is, I think, lanthanum vanadate and bismuth vanadate composite. And the rate kinetics is provided here as zero order kinetics. Reaction rate is this is the whole system where water and air are present in a container. The container is filled with water 50%, and the physics captured in this particular scenario is when the reaction happens, the water converts into hydrogen bubbles and oxygen bubbles. So gas and liquid, this is a multi-phase system, and multiple species are present in this particular case, and bubble dynamics is also involved. So I'll start this animation, and you will see how, with the reaction happening, how the gases are evolving from this system and bubbles are forming subsequently. These systems are simulated for laminar, turbulent, and uh, randomly perturbed system. And in all the scenarios, you can see some of the bubbles are generating, which is highly prominent in high perturbed system. Let's move forward with microfluidics applications. Microfluidics applications are very prominent in biomedical sciences, biomedical engineering, and it is also being used in energy applications. This is a problem associated with leaky gut problem, which is very prominent in biomedical sciences. This red color uh, row is of blood. Above than that, it is gut, and gases are transferring from particular domain to another domain. So this is a mixture of liquid and gas, which is coming in from the inlet. If you see the left hand side, this is a simplistic case which we have simulated. Water and oxygen is coming in from this inlet, and oxygen uh, is transporting due to advection, as well as it is diffusing in the air. So there is a completely existence of two mediums, one water and air. due to the solubility of oxygen in different medium will decide whether the oxygen will diffuse into air or not. There is a term called Henry's solubility or Henry's constant, which decides the solubility of oxygen in different mediums. So these are three images taken at different time. One is for zero point 0.1 second, 2 second, and 5 second, and you see that as water is coming in the domain, the oxygen is diffusing away from in the air domain as well. In the 5 second, it is the concentration, the partial pressure of oxygen is more. This is an animation. This showing you the similar results and how the partial pressure of oxygen is increasing with time. These results are validated with the experimental data that we had gotten. This work was done for US Air Force. Another example of microfluidics is mixing and separation of reagents in a microfluidic channel. These mixing becomes very difficult because these microfluidics channel uh, are dominated by capillary forces rather than gravity forces. So mixing becomes very crucial. Therefore, we apply some strategies such as splitting of the channel or recombining the channels so as the mixing is optimized. The similar strategy we have used here in this particular application. Now let's move towards another segment, which is water. Water has a very high application because it's a fluid, and people tend to simulate these systems before deploying it to the industry. This is a very good application of hydraulic engineering where one person is noting down the consumption of water, whereas uh, one company that we have done this work for, they have designed a flow meter which takes the reading, accurate reading for the water which is being consumed. So the problem with these flow meters are these are accurate when these are provided with a fully developed flow. If there is existence of air in the flow in the water, the reading will not be accurate. So to maintain the accuracy of these flow meters, the turbulence should be minimized and it should be a fully developed flow. So we used a strategy called flow conditioner, which are tend to be used to reduce the overall turbulence in the system and to achieve fully developed flow. This is an schematic representation of the problem. Uh, okay, in the first figure, flow meter is existing right here where my cursor is pointing. And the fully developed flow is achieved in a much later of the pipe, so you need to have a longer pipe to get the fully developed flow. But when you imposed a flow conditioner in this pipe, you got the fully developed flow right here in the beginning, and you can deploy your machinery or you can deploy your flow meter right here to get the accurate reading. That's what the concept was. And if you will see this animation, you will be having more clarity. In the first section, the length of the pipe is much lower than the bottom section. In the bottom section, the gray color is the air. That means at the end of the pipe, there is no elimination of the air is existing right till the end. But in the first section where the flow meter is there and the flow conditioner is there, the fully developed flow is achieved much before. So that is the advantage one can get by doing such simulation. One doesn't have to do so many of experiments before deploying these results. This is the flow around these flow meters, and these concepts are used to reduce the turbulence in these systems and achieving fully developed flow much earlier. Okay, another application is wastewater treatment, which is very prominent and very interesting to chemical engineering people. This is a serpentine channel. This is also called the chlorinated contact tank, where water and the contaminants are in complete contact of chlorine, and chlorine tend to oxidize those impurities over the period of time in this particular contact tank. So when the water exits from this particular outlet, they have a lower concentration of those contaminants. So this system is also very complicated. This is a multi-phase system. Reactive flows are there, multi-phase reactions are there, and multiple species are there. These are the reaction system that we simulated in this particular case. Chlorine consumption, because over the period of time the contaminants are consuming the chlorine and converting uh, these constituents are being converted into some of the byproducts. Disinfection, bacteria is also present as a one of the contaminant, and the bacterial disinfection is also happening. Formation of disinfection byproducts, because bacteria and all these ammonia, all these contaminants, they are converting themselves into the products, and these byproducts can be harmful. So the formation of byproducts are also happening. If you closely observe these reactions, first one is chlorine hydrolysis. Chlorine is coming in contact of water. Hypochlorite is being created, being generated. These are readily involved in the reaction, and these are most highly reactive entities, highly reactive constituents that react with the contaminants and further converts into the products. So that's what is happening in case of disinfectant. These are the entities which are bacterial species, and this hypochlorite is also coming in contact with ammonia, and further the product which is generated from this reaction is further reacted with hypochlorite, and the product which is generated from this reaction is again taken into account as a reaction, and then hypochlorite is also reacting with this, and these are subsequent chain reactions which are happening here. So if you see these schematic, some of them are the reactants, some of them are the products, and there is chlorine which is used as the oxidizing agent. So the contaminants, which are the reactants, they should reduce their concentration over the period of time. The byproducts should increase their concentration with over the period of time. And similarly, chlorine should be consumed and it should reduce its concentration. So that's what is happening in all the scenarios, that with time, the concentration of these elements, these moieties are getting reduced for reactants basically. So this way you can understand the mixing patterns, you can understand the species transport, you can understand where the dead zones are, where the mixing is not happening, and where the concentration of contaminants are low. You can calculate the residence time distribution in this particular domain, you can understand the aeration, and all these aspects you can minutely observe using CFD. These are another application which is algal cultivation. Algal cultivation is very useful, which is an also because algae is helpful in generating biofuels, which was also a part of the conversation in G20 summit. If you have observed something, so this algal cultivation is also very important. These are the moieties which uh, grow, and these systems are analogous to photosynthesis systems because these consume sunlight and convert them to CO2 and water. So these are two systems. One is closed system and one is open system. In closed system, algal cultivation can be produced in a very limited quantity, but in these open system, which are also called the raceway pond, these are used, and these are versatile. These are being explored in a wide manner in CSIR labs, and commercially also these are being explored widely. Availability of nutrients, availability of sunlight, mixing patterns, low shear for the algal species. These are the propellers, and pressure drop across this propeller should be low. So one wants to know all these scenarios, and CFD can be very useful in such scenarios. Another application in biochemical application is design of bioreactors. So bioreactors tend to be used to optimize the microbial growth. So when you provide the interior surface of the bioreactors in a three scenarios, which is flat, positive skewed, and negative skewed, which is the concave and convex kind of structure, the shear stress which is imposed on these moieties can be very different depending upon the surfaces that is being offered. Similarly, that is being simulated here, and the shear stress in case of the sharp edges for convex kind of structure, concave kind of structure is very high, whereas it is lower for another scenario. Now, moving ahead with the reactors, which is one of the most read systems for chemical engineers. This interests them all, uh, is the reactor design aspects. CFD is used in understanding all these aspects, whether the uh, reactor is batch wise, semi batch wise, continuous. It is helpful in all the scenarios. Phases are involved: gas, liquid, solid. CFD is there. CFD is can be used. Reactions: single reaction, series reaction, parallel reaction, polymerization reaction. Homogeneous system, heterogeneous systems. Mass transfer is involved, heat transfer is involved, diffusion is involved. In all the scenarios, CFD can be very handy and very useful. Different types of reactor: fixed bed reactors, fluidized bed reactors, bubble column, trickle bed reactors, venturi jet loop reactors, airlift reactors, ebullited bed reactors, slurry reactors. These all have their own applications in different industries and different uh, productions. Let's say ebullited bed reactors are used in a versatile manner in resid upgradation hydro treating unit, and airlift reactors are used to for microbial growth kind of reactors. Similarly, every reactor has their own advantages in reducing the pressure drop and etc. These are some of the reactors that we have simulated. The first one is a complex system where biomass is being mixed. Biomass, which is lignocellulosic biomass, which when you uh, drop these systems into water, it behaves like a non-Newtonian fluid. So the mixing of these systems becomes rather difficult for a simple impeller systems like this. So that kind of mixing we optimized, and we gave the solution to our client. The second scenario, which is the particles, and this is an inclined reactor which is used in pharma industries and mining industries where particles are involved. These particles tend to move in the downward direction where the rotor is, and it starts mixing. It optimizes the mixing of these particles. The third system in the left hand side is the porous media, where two beds, this is a very analogous system to the fixed bed reactors where your catalyst particles are arranged in a manner and your gas has to pass that particular catalyst bed. Where there, these porous media kind of systems are very useful. This animation I will show you, this is a fluidized bed where air is incorporated into the system, into the bed of sand. from the downward direction, and bed expansion happens, and it reduces the pressure drop in comparison to the fixed packed bed reactors. Another example of impeller rotation is this. This impeller can be used in any system, but the physics, the CFD, which is going on behind this, is very complex. It's not a very simple system to simulate. Another system which you must have observed if you have done any internship in refinery or any other chemical plant, static mixers are very, these are small, but these are very important operations. These systems are motionless. These systems are not mechanically driven, so these save a lot of energy and lot of cost, but these improve the overall mixing of the reactors. So this is a standard Kenix mixer that we have simulated right here. These systems are used to mix gases, liquids, non-Newtonian fluids, and whatnot. So depending upon the internals of the internal blades of these systems, the mixing can be optimized. This system was simulated for brine and water solution, and there are two parameters, which is Z factor and COV, coefficient of variation, which is calculated for static mixer to see how well the mixing has happened. And the results of Paanduv applications, which is done using OpenFOAM, is matching, and the error percentages are comparatively lower. Now moving towards the separation. This is, I think you all must have seen the cyclone separators anywhere in your uh, industries or at your home or somewhere, I don't know, in milling stations. These systems are very prominent, and analogous to these systems, there are hydroclones, which are used to separate solid and liquid systems. Cyclone separators are used to separate solid air systems. When you have a gas and you have some particulate matter, you want to separate those particles from that gas. These kind of systems are used, and the separation efficiency of these systems can be improved by changing some of the parameters such as mass flow rate, some of the orientation, and other parameters. Another right hand side figure is representing the mechanical separation. This is a equipment which is used as a primary separation technique for crude oil and water separation in refineries. You have the crude oil coming in, and then you use these mechanical separators. Depending upon the positioning of this baffle, the density based separation occurs, and the separation efficiency can be improved by incorporating more baffles and and modifying or optimizing the location of this baffle. This system we have simulated. This is a three-phase system, which is very complex in CFD systems, simulating in CFD. Oil, water, and air, and you can improve these separation efficiencies by placing this baffle somewhere here and there, optimizing the placement of this baffle. Now, one surprising element, and which is a booming topic right now, is batteries, which is an integral part or heart of the electric vehicles. So the challenges here are hotspots in the batteries, ineffective thermal management, cooling strategies, cooling materials, thermal runaway. You must have seen all these Ola bikes or different bikes uh, uh, getting burnt, or so many accidents have happened in the recent past, and the problem associated with them was thermal management, the thermal runaway reaction, which is really difficult to control, and people are working towards it, the industry is working towards it. The major concept and major physics here is thermal management. The concept comes with the air cooling technique. When you have a lower capacity of batteries, simple batteries, uh, you can use this technique of air cooling, which is much inexpensive, and you can get efficient cooling using these. Immersion cooling, where you drop your batteries or set of battery pack in a dielectric liquid. When the heat is evolved from these cells, the liquid starts boiling. Once it reaches that temperature, the phase change happens. It converts from liquid to vapor, and that's how the heat transfer coefficients become higher and the efficient cooling happens. The phase change material cooling in this system, the solid phase change material is filled in the gaps of these cells, and once these cells starts heating up, this heat is absorbed by the solid. It starts melting, it changes its phase, and once the heat is absorbed, heat is dissipated, these are again converting into the solid form. Thermal runaway is something that is very uh, important in current scenario, where once your cell temperature becomes higher than certain range around 130 80 90 degrees Celsius, the chain reaction starts happening. The internal components of your battery pack starts melting, disintegrating, and this results into an explosion, a chain reaction explosion, which is called the thermal runaway. So at Pandav, we have a team which is simulating all these systems. Let me tell you something about Pandav, and I think we are at the end of the presentation now. Pandav is a company that was registered in India in 2020 by Advait Gupta, who is the CEO of Pandav Applications. He's a master's graduate from Stanford University, worked in 7 years in US in a CFD commercial company. We are a team of CFD software developers, application engineers, and scientists. What we do is we develop CFD softwares. We we try we we migrate people from commercial softwares to OpenFOAM. We do CFD consulting, we do CFD training workshops, we do CFD DEM, all the aspects of computational physics we cover. We work on tangential technologies like AI. We integrate CFD and AI to shape a software which has a graphical user interface and deploy them to industries. We are working on different industries: water and environmental, chemical, oil and gas, 3D printing, aerospace, energy, defense, microfluidics, consumer products, automotive, turbo machinery, HVAC. And technology side, we are working on different technology as I have shared. This is our office located in Bareilly, Uttar Pradesh, and don't hesitate to contact us in case of any confusion, any query about the CFD. Now, as a student, you should all be worried about CFD market and job prospect in this particular domain. Let me tell you, every industry at the moment is trying to get a CFD, an integral part of their workflow, as a core R&D team. Battery, electric vehicle, these are some of the booming topics where CFD is highly prominent. People are also gaining interest in open source community, and the demand for open source software is increasing day by day, and industry is also appreciating the knowledge of open source software, and they are not hesitant to migrate to open source community, open source software. And the growth rate is around 5.33%, and it is going to be much higher in upcoming time. These are some of our initiatives. Paanduv Applications Advanced Academic Program, where we teach students CFD using OpenFOAM. We give them some of the major booming topics related to battery, related to water, hydraulic systems, and we teach them these aspects as well. This is something that we have launched last year, International Simulation Olympiad, and we have gained enormous interest from India and abroad. The winners for 2022 uh, ISIMO were Cranfield University and IIT Bhubaneswar. And I would really appreciate Nirma University if they take part in this year, and this will be a great moment for us, for them as well. So the tentative courses modules that we have, it's just a brief. You can go to our website, look at all these aspects, all the course structure that we are providing. 10 hours, 20 hours, and 30 hours are some of our modules, and we include some of the case studies that will be very important for all of you guys. And as a cordial gesture, in collaboration with Nirma University, we are providing all of you a 2 hours free workshop on OpenFOAM with CFD with OpenFOAM exclusively for all of you guys for Nirma University. And we are also promoting, if you have any interest in internship opportunities with Paanduv applications, we will look at your resumes, and we will consider them. So to access the free 2 hours workshop, you can go to our website, academic program page, and we have created a tab of Nirma University there. You can directly click on that and fill up your details, and we will tell you in October first week, we are going to have a new session for OpenFOAM training. So you are all cordially invited to that training. These are some of our clients, and we are trusted by them. Some of them we cannot even name, but it's always great to be associated with companies like that and with universities like Nirma. Thank you so much. I'm open to questions if you have any.
Students, if there are any doubts, you may please ask. Anybody? Yeah, I think students are not having any doubt, but I do have some points, not exactly doubts. Like, before I heard about CFD many times. I've never worked with it. I had an impression that CFD is all about meshing only. There are no reactions. There is no, core chemical engineering. But within a span of 1 hour, like, you could make things very clear that, CFD is not only about meshing and only study, fluid dynamics. Though fluid dynamics or Navier-Stokes, as you mentioned, is, key to it. But then it also, touches so many core areas of chemical engineering. So apart from that, I think I must compliment you for the session which you have conducted, because in a very nutshell, without going into the details of how to simulate, right, you have been able to provide all the information which you wanted to. And also, I would like to thank team members of Paanduv, that you worked at backend and you created this 2 hours of special workshop, and you already created the link. So it's a really a great gesture on your side, and we really appreciate that, and we'll make sure that the students take benefit out of it. So thank you very much for your time. And I would again request Arya was the one who introduced you, just for your information. So I would like her again to conclude the session. Thank you very much. We'll be keep in touch.
Thank you so much, sir. Yeah.
On behalf of the Chemical Engineering Department, Nirma University, I'd like to extend my heartfelt gratitude to Ma'am Dr. Rimzhim Gupta for sparing time from her busy schedule and gracing us with her words of wisdom. Thank you so much, ma'am.
Thank you, Arya. Thank you, all of you, to have patience and listen to this webinar. Thank you so much for your time. Bye.